All right, so in this video, we're going to be looking at calculating the area under a parametric curve. So in this case, we have this parametric curve defined both x and y in terms of t, and we'd like to find the area under the curve and above the x-axis. So the first thing that we should do is we should plot the graph. And so this looks so much as something very much like a parabola. And the way that we determine the values of t that are going to be our bound, since they're not specified in this particular example, since we're intersecting with the x-axis, we would want to know when the y function is equal to 0. Now, in many of these problems, they will tell you the values of t that they want you to do the integration under. But for this particular example, they're not specified, and so we can go ahead and we can find them. We're going to set our y function equal to 0, and then go ahead and do the algebra to figure out where that's going to happen. And then when we divide by 4, we get cosine 2t is equal to 1/2. And what are the angles where cosine is going to be equal to 1/2? Well, that's going to happen at pi over 3 and negative pi over 3. And that means that t is going to be negative pi over 6 and pi over 6. So those are going to be the limits of our integration. And if you go to a parametric curve grapher and you double check this on this particular website, you can do the slider. You can see that as you cross over, pi over 6 is about 1/2. It's a little bit more than 1/2. But as you cross over between these two, that's the positive value of pi over 3, pi over 6 in this case. And then on this side, that's the negative value. So the graph goes like this. So we're going to go ahead and set up our integral. Now, to do the integral for the area under the curve, we are going to integrate between our two t values. So negative pi over 6 and pi over 6. The function that we're integrating is the y function. So for cosine of 2t minus 2, and then we have to multiply by the derivative of x prime. So our original x function was 2t, so we're going to multiply by 2 cosine t dt. So again, our general formula is going to be alpha beta of y of t x prime of t dt. So this is our y, this is our x prime, and then our dt. Now, we're not going to be able to integrate cosine 2t times cosine t as is. So what we can do is we can use a trig identity in order to replace this with something in terms of just cosine t or just sine t. The choices are really kind of up to you, but I'm going to use the sine squared identity. So this is going to become 1 minus 2 sine squared of t. And so we're going to need to distribute some things. So let's see what happens when we do some distributing. So first thing, we're going to distribute this 4 through this parentheses. So that's going to give us 4 times 1 is 1, and 4 times 2 is 8. And then we're going to be able to combine our 4 and our 2. So 4 minus 2 is going to give me a 2. And then we need to distribute the 2 cosine t through this integral. So 2 times 2 is going to be 4 cosine t, and 2 times 8 is going to be 16 and cosine t. And then we just have 2 terms, and we can take out the parentheses like so. Now, the reason that I chose the sine squared identity was because I knew I had this cosine here. And that meant that I can do a substitution on this term and integrate as sine as u and cosine as du. If I had chosen the cosine identity, I would end up with cosine cubed, which I would need to then apply a substitution for in order to turn 2 of those cosines into sines anyway. And likewise, if I had used the cosine squared and sine squared, then I would have one term that was like this, but then also another term that was cosine cubed, and I would still have to convert it to sine squared. So by using this particular version of the cosine 2t identity, then I was able to essentially have all that algebra already completed for me. So again, this term right here is going to integrate very nicely. This term is going to integrate by doing a substitution. Now, one other thing that we can do is that both of these functions are even. This is an odd function, but squared, and this is an even function. Squared functions are even. This is even. Cosine is even. So the fact that this is an even function means that I can change my order of my integration and double it so that after I do after I do all the stuff, I'm putting 0 into my functions, which is going to be a lot easier for me to evaluate than trying to deal with the signs on plugging in pi over 6 in both cases. So now I'm going to go ahead and do my antiderivative. And again, for the second term, I'm going to do u is sine t and du is cosine t dt. And the first term, I don't need to do any of that for. So I'm just going to get 4 sine t minus, this is going to become u squared. The sine squared is going to become u squared. So I'm going to get sine cubed of t. And so again, we can just make this a little clearer. This is u squared once we do the substitution, which is how we're getting u cubed. And because it's a definite integral, we're not worrying about the limits here. But that's where this 3 comes from. That's where the sine cubed comes from. And then we're going to evaluate this whole thing between 0 and pi over 6. Now, if we plug in sine of pi divided by 6, we're going to get 1/2. So this is going to become 4 times a half minus 16 cubed and 1/2 cubed. And then when you plug in 0, sine of 0 is 0, sine cubed of 0 is also 0. And so that's why we did the symmetry. And so we're ending up with 2 minus, let's see, 1/2 cubed is going to be 8. So that's going to be 2/3. And 2 minus 2/3 is going to be 4/3. And that's going to be 8/3. And so that's our area under this parametric curve.